Hi, I am Jeffrey.
Make the ground shake.
Now, in this video, we're gonna talk about the first two stages of matter we'll cover in this chapter: liquids and solid, collectively known as the condensed space. I want to explain this today. It's about the solids, general properties, types of solids, and crystalline and amorphous, and about the liquids, its general properties, its viscosity, cohesion, and adhesion. Now we talk about the solids. The first solid have general properties. The atoms closely packed together, and the atoms have regular rigid or rigid pattern. Types of solid. We talk about crystalline solids. Atoms or components arranged in a regular geometric structure. Geometric arrangement at the atomic level often dictates the geometry of the natural crystal. We have an example about the cubic, a simple cubic about a pyramid. Types of solid. The second is unit cell, smallest groups of particles in crystal that have the complete repeating pattern. The second, many different types resulting in many crystal shapes.
Now we talk about the second, the amorphous solids. Solids matter with a regular recurring pattern. The example of the glaze in the tire of the core, you have a hard material. Now we talk about the liquids. General properties of liquids: atoms are still closely packed together and no regular pattern. That's different with solids which have a regular pattern. The solid have general properties too. The shape of its container defines volume, no rigidity, and faster its molecular movement than solid, but still slow. Now we talk about viscosity, a measurement of the resistance of liquid to flow, the amount of frictions between liquid particles that resist changing the shape.
Okay, now we talk about expansion coefficient and isothermal compressibility derivative. We will to derive between coefficient alpha. We will to derive coefficient of alpha and isothermal compressibility K sub T. Your mission, should you choose to accept it, is to show that the partial derivative of P with respect to T at a constant volume is equal to alpha divided by K sub T. We need to show that derivative of pressure divided by derivative respected to temperature with the constant volume equal to alpha divided by K sub T. When we write show, it means exactly the same thing as proof, so like to alternate the words because they mean exactly the same thing. Both show and proof need proof. Recall that the alpha equal to 1 divided by volume times derivative of volume respective by the temperature with the constant pressure will be transformed. We will transform this formula to be alpha times volume equal to derivative of volume respective by temperature with a constant pressure. And now we recall too about K sub T isothermal compressibility equal to minus 1 divided by volume times dV respective by dP with the T constant. When we transform it to kT times minus kT times volume will be equal to dV per dP with T constant. The volume of a system can be thought as function of two variables and temperature. Importantly, the volume is state function just like the internal energy and the enthalpy, so that means we can write an expression for the exact differential of the volume in terms of the pressure and the temperature. And we know that the form of coefficient of dP and dt have to be a particular form. We have a partial derivative of state function with respect to that particular variable. So we have dP plus something with dt in here. So with respect to here, and that we have to have the partial derivative phi with respect to the temperature as coefficient here, and since the pressure is changing, you have constant temperature for this particular. So we have dP respective by pressure with a constant temperature, and we have derivative particular by volume divided respected by the temperature with a pressure constant. Next, we want to divide each side by dt, and after that, next we are going to impose a condition of a constant volume. So we will divide this both of sides with dt. So we divide this by dt, we divide this by dt, we divide this by dt. And after that, we impose that formula to volume constant. So we write down here dV divided by dt with a constant volume equal to dV divided dV with a temperature constant times dP divided dt with a constant volume. And we leave this because dt divided dt is 1. Derivative of particular of v divided by dt will be with constant pressure. Now this is so interesting partial derivative change in the volume respect temperature under a constant volume circumstance to either v constants tell us the derivative has to be exactly 0 if you have a constant. So we can write here it should be 0 equal to dV divided by dP with a temperature constant times dP divided dt with a temperature with a constant volume plus dP dV by divided by dt with a pressure constant.
So we can move here to outside to the bottom of side A. We can move that to be minus dV divided by dt with a temperature with a constant pressure equal to dV divided by dP with a temperature constant times dV per dt circumstance V. So we can change this to be minus alpha, and we know that alpha V we have to change this to be a minus alpha. Because of this, alpha times V dV per divided dt with a pressure constant, so we can change this to minus alpha per P equal to per V equal to dV divided dP with a temperature constant times dP with a respective temperature with a constant volume. And after that we changes to isothermal compressibility, mean alpha minus alpha times volume equal to minus K sub T times V times dV per dP with a temperature constant. So we change this to be a minus of kT times V. So we know that after this, minus alpha times V divide kT minus kT times V equal to dV divided by dP with a temperature constant. After that we leave it the minus and we leave it a volume, and we know that it will be show that we can show that the start from this we can prove that why what from this formula, how come from this formula.
Okay, now I will explain you about the third subject, exactly about the sublimation, vaporization, and melting about or heat up fusion. Now, but first I will explain to you about every phase changes. Liquid to solid, its transformation is called freezing, and solid to liquid is called melting or heat of fusion. The third is liquid to gas or vapor is called vaporization or heat of vaporization, and gas to liquid is condensation. The fifth, solid to gas, is sublimation, and gas to solid is deposition. Now after that I will explain you about vapor pressure or gas pressure. I have formula from Stefan-Boltzmann is P equal to B exponent W divide RT, where B is another constant, the energy of vaporization. As we shall see later, the molar heat of vaporization, key vaporization, is related to W by key vap RT. Putting this value of V of W in the expression for P, we obtain pressure equal to P unknown exponent key vaporization RT divided by RT, where P unknown is also constant. The constant P unknown has the unit as P and can be evaluated in terms key vaporization and normal boiling point T sub B. At T sub B, the vapor pressure is 1 atmosphere. So 1 atmosphere equal to P unknown or unlimited exponent minus key vaporization divide RT sub B. So after that we go to logarithm. We logarithm all of this, but we change into P unknown or unlimited equal to 180 m times exponent of plus key vaporization divide RTB, and after I will logarithms, and we have ln pressure equal to minus key vaporization divide RT plus ln P unlimited. So that's all from me. This is the end of this video. Thank you.